said it. He was just like sitting in his nose.
Yeah, but you don't like it when it's
Screw that! The only thing that matters, grades do matter in order to get academic scholarships, but the GPA is so low, the requirement, it's like, you can be at like a 3.3 and still get like a $14,000.
It's pretty sad. For example, I didn't really have that good of high school grades, but then I went to a junior college. It was so easy, and I had like a 3.99, and when I transferred that into Northwestern, they gave me like $7,000 for having such a good GPA. It's like,
Did you work harder in JUCO than high school?
I worked on the stuff I wanted to, but I also probably wasted half of my life playing video game my freshman year of college.
World
of Warcraft! You'll find, guys, that you have way more time in college than you do in high school.
Okay, it's different.
Yeah. I would assume that's true though. Like, I'm involved in a lot of
Way more time, because you only go to class like 3 hours a day.
Wait, let's look at our schedule today. What classes are you going to? Steven, let's have a look. I'm already freshman year of college.
How many credits do you get?
School from 8 to 3 credits. Yeah, whatever. I did some pictures. Maybe not an hour.
You don't know how many credits and you set it all up? How's that possible?
Maybe that's
I
why.
set it up.
Choose that.
I'll get back to you.
There's no way, because like 3 hours a day would be probably about 16 credit hours. Because you only have Monday, Wednesday, Friday, or Tuesday, Thursday classes.
And then 6 to 7, 15 minutes. 8 to 3, 1. I'm so sorry. And then like, you have to stay a little bit late after for like pictures.
Do you actually?
you say, oh,
And then you're like,
I'm sorry, I'm a guy.
Lauren!
Or I'm sorry about until about
No permission
7:30.
to
And
say
then I
that.
get home like 8.
No, I'm not gonna miss this one.
So,
I will say that when I was in college, I would have had teaching. That's what my life was like when I had a teaching.
Stop!
Get like 200 observation hours in.
I'm sorry.
So on top of like, so I had all my classes, and then I played basketball in college, and then so like I would literally wear a suit the whole day long. It's like I go to class, then I go straight and observe a high school, and then I go back to class, go observe a different high school, go to basketball practice, take off my suit, practice, go home and study and do my rest of my homework the rest of the night. Yeah. Okay, so guys, let's get into circular motion here. Okay, so as the name implies, we're now moving how? Circularly. In order for us to understand circular motion and a concept called centripetal acceleration, we need to understand a few other things first, like tangential speed. It's a fun word to say. Everybody say it. Tangential. Stop! That's not okay!
You just mixed 2 letters.
Yeah!
Whoa! Hey, Cranes, make him repent right now.
Repent!
Get on your hands and knees
Who
there.
came up with that? Was that you?
No, that was not me.
That was actually like 2 months.
I was like,
Sorry, it was transgenital.
Stop it! You guys are so bad little kids.
So bad little.
You bad little kids.
So bad little kids.
Sinners. Okay. Okay, so what tangential speed is? Now notice it doesn't say tangential velocity. Okay, I'm just going to say T speed from now on.
Okay, that's way better.
T-Swift.
Like tangential.
Because we're not going to deal with direction, because when you do circular motion, you're always changing direction.
Whoa.
What? Yeah. If I'm going in a circle, my direction's changing every time I move.
That is the Earth on southeastern west. What does that mean? That's the stupidest calling that out. Because the Earth is going in a circular orbit around the sun.
Hey, come on.
shower.
It says tangential, so one tangential speed is an object, when an object is in circular motion, listen, come on. We only have 15 minutes left.
Oh.
We have 2 problems to get through and all this stuff. Okay? So if I take something that's going in circular motion and I take a line and run it tangent to its path. You guys know what tangent, running a line tangent to its path is, right? I think you guys have a picture on your.
Yeah.
Yep. Okay. So I'll wait till we get to that to kind of explain that a little bit more. I'll explain that in a little bit. But so your t speed is going to depend on how far you are away from the center of the circular path. So can someone explain why distance away from your center of pivot point of circular motion, why that would affect how fast you're going?
No, because like,
Gravitational pull.
Say that again?
because like the farther away you are from things, the faster to keep up. Like,
Okay, imagine this, a carousel.
wing
Okay, you've got an inner lane horse and an outer lane horse. Yeah? Okay, can you imagine a carousel with me? Okay, when that thing's going in a circular motion, one of those horses has to travel faster. Which one has to travel faster?
The outside.
The outside, because it has to cover more
It's
distance.
like a track and field thing.
It is like a track and field thing.
No sense.
Because if you have like something on a street.
No, but it's farther away. It's like,
Okay, so let's say, right, this is the path of my here's your center. This would be like the path of your inside horse, and this would be the path of your outside horse. Which one has to cover way more path or distance?
The outside.
The outside does. So the further you are away from your pivot point, central pivot point, the faster you have to go in order for you to maintain that circular path.
But wouldn't the inside one go separate?
So you're saying the horses on the inside one are traveling a lot, and like the ones here are like behind, so the inside one is passing the outside one all.
It just seems like if I'm picturing like if I had something like on a string and I do a small circle, it's like going faster than if I did it in a big circle.
That is true. That's kind of.
Did you ever have
Yeah,
a
but
thing
that's
like
only
on a
because your
pendulum?
forces aren't the same in that case.
It's like when you're swinging a kid around. And it gets slower as you go further out.
It's because of the force difference. But if you apply the same force, I know what you're saying. But you're applying the force.
You feel like go faster and
Yeah.
then you like let their arms out again.
I know what you're saying.
because you control center of gravity.
Okay? Now, when you have your t-speed constant, you're in uniform circular motion. We're going to talk about uniform circular motion. That's going to be where we're going to kind of camp. And the reason why is, again, it makes things a little bit easier. Okay? So when you're going in a circle, we're assuming that our speed is constant. Okay, now this is where it's going to blow your mind a little bit. Your speed is constant, but you're always accelerating.
Oh my
Because you're always
Lanta.
changing direction.
I think one.
Isaac, why are you a professional physicist?
I'm just gonna start keeping track of this.
Let's see. Vital.
Stop.
Don't accelerate. No,
Oh, you mean
accelerate.
Assumption of the
And
worst.
this is-
we assume that them like
Stop.
Your acceleration is all going into changing your direction.
What did I
Physics we
say?
assume more than like.
Ask him.
Isaac, what'd you say about it?
It's always changing direction, so it's always going to have a
I don't really have time to
Because it's-
for you to update.
circle.
No. Wait, so what did you just say we're assuming on the other?
That we're.
Uniformity. That's always constant. If we're talking about
Every
uniform
time I
circular
write
motion.
I'm like, what? Or like, where did
I forgot what it was.
Site uses a plugin that they show Firefox.
I'm trying to like.
Alright, ready, here we go.
A car moving in a circular path experiences acceleration even when the speed at which it is traveling remains constant. This is because acceleration depends on velocity, and velocity is a vector with both magnitude and direction. When the car moves in a circle, the direction of the velocity vector is constantly changing. Therefore, the acceleration, or change in velocity over the change in time, is also changing. Acceleration of this nature is called a centripetal or center-seeking acceleration. When the radius decreases, the direction changes more quickly and the experienced acceleration is greater. When the radius increases, the direction changes more gradually and the experienced acceleration is not as noticeable.
That's what I was talking
In other words, AHC.
Yeah, it's not as noticeable, but they're going, the speeds, so it just looks like it's going faster because it's covering less ground.
Wait, so it said that acceleration is greater when it's a smaller circle, but don't you need more velocity when it's a bigger circle, or like the circle bigger, so why would the acceleration be bigger?
Because because acceleration is 100% due to your change in direction.
Oh.
And you're changing direction faster when you're in a smaller circle than when you're in a big circle.
So wait, like theoretically, if you have like a circle, the bigger circle is the more flat it is, like the more straight a circle is, the bigger it is.
Yeah, I suppose. The bigger your circle, the more you don't turn as much. Your distance traveled, you don't turn as much when you've got a big circle than if you have, a little tiny circle where you're constantly changing directions like really, really quickly.
Or the smaller the
object.
For the big circle.
Okay, so here's your centripetal acceleration equation, and remember, I think it said on the little visual that centripetal means what? Center seeking. And so when you're going in circular motion, you're always accelerating towards the middle of your circular path.
Oh my word. My mind is
No.
Okay?
It's the same word.
So if I've got a circle here and an object, its tangent, its t-speed, is going to be like, if I were to like let go and it would just continue to go straight, that's what its t-speed would be, but it's always accelerating towards the center. Otherwise, it would no longer be going in that circular motion. I'll show you that with vectors a little bit later, okay, but that's not right now.
So what did I write down?
You will not, you'll just do it based on sign. There's no like north, south, east, or west.
Just like
Okay, so it says the acceleration of object moving in circular path at a constant speed is going to be 100% due to its change in direction. Okay, because if we're going at constant speed, we know that it's not accelerating because of its constant speed. It has to be because of something else. Okay, and you remember what happens to the sign of velocity if you change directions?
It switches.
Yeah, it can switch, right? So would that then affect what your acceleration would be?
Amen. Please don't hurt yourself.
Okay. There's weird like bones for my finger.
James, you don't have to do it.
Don't.
Never touch it.
Feel that?
Oh yeah, it's not on the side. I feel like the pointy.
Grave says it's
No idea. I think I got a tumor on my finger. It really hurts actually. So here we go. We got your tangential speed squared divided by your radius. Is how we're going to figure out our centripetal acceleration. The higher, the bigger the radius, the less acceleration. That should make sense because if that we got these two circles and the radius is smaller here, which means it's going to change more direction quicker, meaning it's going to accelerate more.
Yes. That makes sense.
Okay?
So then will the
But then here, it's further distance. Okay? So that means it's not going to accelerate as much, aka it's not going to change direction as quickly. It doesn't have to.
It's less acceleration, but more speed.
and over a longer period of time?
So technically I have less acceleration here,
But faster.
but it would be moving faster. Because it has to cover more distance in the same time period. Okay, I know it's difficult, I understand.
No,
Wait,
I
what's the
wasn't
little
there.
t under the tree?
Tangential, because we're gonna talk about different type of one later. Okay? Okay, now this kind of gets more into like derivative stuff and like calculus related stuff, but I'm just gonna kind of show you how this would work. Okay? Now, if you take too big of differences, it's hard to see this, but if you take 2 points that are relatively close to each other, okay, so this would be like the tangent line here. So that would be your t-speed. Okay, t-speed at A, t-speed at B. Okay, those you could act like vectors because we're talking about velocity here, correct?
Sure.
Okay? And remember, when we're trying to find change in velocity, it is final minus initial, correct? Okay, so if I take these two vectors, I take my final vector and subtract my initial vector from it, that would flip it, correct? And you would add it tip to tail. That's what they're doing here. Your final vector is the same direction and same magnitude. You see it?
I do see that actually.
I will in a second. Okay, so the VF and the VF are in the same direction with the same magnitude. Does everybody see that?
Yes.
Okay? Since we're subtracting, because change in velocity is VF minus VI. So here's our VI vector. When we subtract it, we flip it, or we add its opposite, remember? Okay? So we're adding its opposite tip to tail. So it's the same magnitude, but it's flipped. Does everyone see how it's now flipped?
Amen.
Yeah.
Notice where the change in velocity vector is located.
So it's
Towards the center.
What is that?
That's not the center. Well,
Question.
Yes. What's your question?
Mine? Okay, is the line between A and B the same as change in velocity line? Or no? Would that-
Line between like this?
Yeah, would that give you the same number?
No. If you did calculus, probably.
I just wondered.
Probably. Yeah. But I don't do that in this class. So I don't know if that.
And also,
It's
isn't that
advanced.
just like a way to show that the math works out?
Yes.
Okay.
Yes.
Wait, so why is that?
Why is what towards the center? Yeah, like if I were to take this and add my two vectors, it's going to be towards the center of the particular circle. Okay, now it's hard for me to actually kind of show that up here, so I took it and they brought it down. And also, that technically, the further distance you get away, the harder it is to see this. You're actually supposed to take like really small pieces, and it works better. But I wouldn't be able to show that very well. Okay. Because technically, I have quite a bit of change in direction from here to here. There's a good amount of change in direction there. But anyways, okay. So the bullet point there is really what we need to focus on, that our centrifugal acceleration is always going to be directed towards the center. I'm trying to think here. I think I didn't need to go that far. This is probably tomorrow.
Oh, wait.
We have two problems to do. We'll do it quick. Hey, stay with me here. This won't take very long. You'll find that this math actually is pretty simple. Okay, so we have an equation that is your centrifugal acceleration, your tangential speed squared, and your radius between your point of movement and your center pivot point. Okay, it says that I have a circular track. The car, if the car is 48.2 meters from the track center, what is that going to tell us?
The distance.
The radius. So 48.2 meters. Okay, if I were to draw a picture, that would be its R, and that's 48.2. Okay? It says the centripetal acceleration. So which variable is that? AC is centripetal acceleration, C is centripetal, A is acceleration. Then you solve for VT. Multiply, take the square root.
So tangential speed is VT.
Yep.
Oh, why'd you write the V so small?
Because I wrote T first on accident. Yeah, I didn't mean to make the T so big.
So did that, I'm sorry.
What?
Whatever that word is.
So you're in this particular case, when you multiply here and take the square root, what you end up is a meter squared per second squared. Take the square root of that, you're just with a meter per second, which is what velocity is.
What was Bryce's comment?
Okay, because you multiply the meters.
Yeah.
And then you
He said,
Yes.
he said you don't have north, south, east, and
No, we're halfway through this section, but we're where we need to be.
Kramer, what's it like?
No, tomorrow you will have homework. You'll have homework today and tomorrow.
What's
I understand it's
Homework
not.
today is on your very first page.
If you
Okay, so let me show you. This is meter per second square, and this is a meter.
Bryce, you're
Correct?
so smart.
You multiply those two, you get a meter squared per second squared, correct? And if you take the square root, that gets rid of the squared and the square, and it's just a meter per second. It doesn't kind of agree with what.
So I don't want to be late.
Yeah, you're gonna get like.
The answer is 19.7 meters per second. And the next one is just the same, except for you're solving for acceleration, which is way easier than.
Stop!
So are we staying on the system tomorrow?
No, I'm doing this part two.
Masapi.
Yay, almost got.
Love you too, Shy.
Oh, Stevie Wilson.
We killed it.
Yeah.
Oh, I have 1 minute.
We had homework.
No, I had
We
test.
had.
No.
No, like for today.